So we have a good crowd here. Okay, awesome. Now let's start recording.
We're live.
Yeah, we are certainly live.
Can I do a quick plug for the office hours call then, seeing as now we're on video?
We're live and now we're recording.
Wow.
So hello everyone, welcome to the IPFS weekly call, where we get to see the great things that are being built on top of IPFS. Today we have a presentation about Keep Network, but before we begin with our main presentation, Ali has an exciting announcement.
Apologies for the people on the call, we've now heard this 3 times, but IPFS office hours is a thing that happens just before the IPFS weekly call. So you missed it because the IPFS weekly call is happening, but it'll happen again next week. And if you're interested in contributing to IPFS but don't know where to get started, or you're running it in production and you've got some questions, like, we're there to help. We are available to talk to you. Come chat. Anyway, thank you very much.
Awesome, and once again, Ali, thank you for doing this. This is great. All right, so we don't have any more announcements, so we will start. And today's presentation is about Keep Network. Keep Network is an off-chain container for private data. And we have Raghav and Piotr here to tell us and talk about Keep Network and how it's using libp2p. So without further ado, Raghav and Piotr, thank you for being here. And I will turn it over to you so you can present. Thank you.
Thank you, Portia. Thank you for inviting us. We are really excited to be here with you. Can you see my screen?
Yes.
Okay, awesome. So my name is Piotr, together with Raghav. We would like to give you a presentation about how do we use libp2p in Keep Network. We will first talk about what is Keep and how it works, and then we talk about how do we use libp2p. So jumping to Keep. If I had to describe Keep in just one sentence, I would say that Keep is a privacy layer for public blockchains. Over the last few years, public blockchains brought incredible transparency and auditability with immutable and censorship-resistant records. However, any smart contract that is published to the blockchain can be easily accessed by competing interests. So when companies consider building applications on blockchain, privacy is one of the primary issues that arise. And Keep is a bridge between public blockchain and private data, so public contracts can harness the full power of blockchain technology without compromising on transparency and privacy. We can also say that Keep is a form of a private computer able to store and compute data hidden even from itself. One of the underlying primitives of Keep Network is the random beacon, which is responsible for providing a trusted randomness source for public blockchains. We can divide Keep Network into 2 parts. The part that we call on-chain is a set of Ethereum contracts that serve as a kind of an API to our network. The second part that we call off-chain is a connected network of Keep clients, which use special communication protocols to serve requests from the chain. For now, we can focus on random beacon because from the perspective of libp2p, we will use pretty similar mechanisms for all other features of Keep Network. So the way random beacon works is that external client publishes a request to the chain. The request says, please produce a random number for me. Keep clients receive this request from the chain, and subset of them, those clients that are in the group, which is the chosen group, cooperate to produce a random number. The way this cooperation protocol is designed does not allow anyone to influence the result, and the result can be later cryptographically proved to be free of manipulation. So Keep clients publish the result to the chain, and they start another protocol called group selection that will allow them to elect a new group, and this new group will be added to group registry, and this new group, may or may not be asked in future to produce a new random number. This is also kind of random, which group is chosen. So if you look at it from off-chain perspective, this part that is connected to the chain, we have clients connected to each other using libp2p. Inside this network, clients form groups. One node, one peer can be a member of several groups. Clients, peers communicate inside those groups. Groups are chosen randomly, and they have a limited time span. From the perspective of the network, we need the following properties. So clients must be able to efficiently exchange messages inside those groups. Messages must have a very, very high delivery rate inside the group. Some communication in the group has to be public. Some communication has to be kept private between two clients. We require message attributability. So sender must be well-defined, and the message must provide sender's attestation. We require integrity of messages. So we need to be able to detect a message was tampered. And we need a peer discovery mechanism that when a new client joins a network. So libp2p, and specifically the PubSub implementation, ended up being decided as the best option for us, mainly because client is written in Go, our client is written in Go, and libp2p was actively developing Go IPFS and Go libp2p suite of libraries. Now Raghav will present how exactly it looks under the hood.
Right, like so Piotr said, when we started this adventure about like a year and a half ago, the options were really libp2p, Go Ethereum's discovery code that they have, and then rolling your own. And we decided to join libp2p and IPFS because they had quite a bit of traction. And so how we use it in our code is that clients come in with an Ethereum account. These are ECDSA keys. And so we have interfaces between our Ethereum code and our libp2p code. And we take these ECDSA keys and we turn them into the libp2p representation. And then from there, we get our peer ID. And we also use a listen address. We use DHT hosts, custom transport. So we instantiate all this stuff. And that kicks off our network. That allows the client to connect to the libp2p network. And then going to the next slide, you'll see that what we do from here is that clients need to find a bootstrap list. And so we'll publish a bunch of bootstrap nodes. We're a little worried about this because they seem like DOS vectors, but we'll publish these nodes. Clients will connect to the bootstrap nodes. One of the things that we need to do is ensure that there's a good diversity of bootstrap nodes that clients can connect to, also retries and things like that. One of the interesting things that we got to do is that we wrote our own custom transport to hijack a connection before the key client joins the network, the libp2p network. What we do here is we get the connection, we check the stake to the peer each other's stake chain. Then they do a bit of a handshake, like a little bit of a challenge response. And once they've authenticated each other, then they're like, okay, you're good to go. You're good to join the network. So Piotr mentioned that we have a group selection protocol. In that group selection protocol, clients basically submit tickets on the chain. They're validated. They're like, okay, these tickets are good. This is how many shares you get. And that allows you to join the PubSub channel. And so basically the PubSub channel is just like a randomized word. It's just a hash of all the clients, and they join this channel. And every group is its own PubSub channel. This is a topic in Go libp2p PubSub, so we just form that topic. And we currently use FloodSub. We've played around with GossipSub, but we want to initially go with FloodSub so that there's a good, diversity of messages hitting all the peers. And if we see that EpiSub or GossipSub are better for a use case in the future, we'll move to that. So sending a message, and the next few slides are a little bit out of date because we updated libp2p to take advantage of the strict signing and verification. So what we do is we just, we get this protocol message, whatever protocol the clients are executing. So there could be DKG or relay signing. And what we do is we marshal the specific protocol message. We register some handlers. and then we just send it. We just call publish. We no longer have our internal signing code. We just gutted all that out, and we're relying on libp2p for signing the message and verifying it. And so this is what the message layer looks like. Again, we use protobuf. You'll see the libp2p pub/sub message, and then you can just ignore the network envelope because we removed all that, and now it's as simple as the network message itself. Right, and so for receiving a message, we basically call next, which is a method that the pub/sub interface exposes, and every message is basically treated like an HTTP request. We're like, okay, this is a new Go routine, process that message, and then call the correct handler to send it to the correct protocol to execute. Right, and so we also wrote a little bit of custom code, for example, handling the different key types, but again, we primarily focus on ECDSA and ensure that they're interoperable with each other. And we have some custom handling code as well. Right, so things that we need to do or that we could use. So one of the things is that we need deep connection management. I believe this is going to be possible with the connection manager, but I'm not entirely sure. The reason we need this is to disconnect clients that fall below the staking threshold. Also, if we need to disqualify peers a given round of the protocol. So we need something that can let us like ban connections or cut them or sever them for some period of time. We need more resilient bootstrap, as mentioned before. So that's to ensure that we get a good diversity of bootstrap peers. And then we need to have a retryer. There's a few options here. We could have something as simple as just like retrying code, or something a little bit more complicated like what HashiCorp implements in Swim. And the last thing is this rework validation pipeline in Go libp2p pub/sub. So currently we're anchored to a commit that is in PR review. This is because after updating to strict to enabling signing within Go libp2p pub/sub, we noticed that some of us could run our end-to-end code, our experiments, and some of us couldn't. And we noticed that once we enabled signing, messages had a higher frequency of dropping for some folks on our team. And we finally realized that it's because validation was happening inline, and this commit right here splits it up into synchronous and asynchronous validation, which allows messages to be processed. So expensive things get pushed off async, and then basic structural checks happen inline. And it would be great to get that merged in ASAP so that we can be back on master. Yeah, so thanks, that's our implementation. Hopefully that was good enough information.
Awesome, thank you very much. Do you mind? Awesome, great. Thank you very much, that was great. Okay, next is Q&A. So if anyone has a question, if they could put it in chat, that would be wonderful. So are there any questions regarding network and libp2p implementation? I have one question. Could you tell us on like a higher level, who is using like the Keep network? Like when they're building a smart contract and they need the Keep network and they need to have a public contract, but a private container of data, like what are the use cases that you're seeing initially?
So we're going to be launching our private testnet pretty soon here. So we haven't launched yet, but the folks that we're looking to work with are folks who need these private containers. So like, Aragon or a few folks like that are pretty interested in these use cases. Folks that need decentralized custodial solutions would be very interested in this technology. One of the keeps that we're looking at, and Piotr's given a few talks on this that you guys can find online, are TECDSA keeps, threshold ECDSA keeps. That's going to be our first type, and we're actually building our first product in that, which we'll announce more on that later. So anybody who needs a decentralized custodial solution, anybody who needs private containers for data, that could be interesting to mask some information from some period of time. But initially, we're just focused on TECDSA keeps. So anybody that has a private ECDSA keep that needs to be remote controlled or kept securely on Ethereum.
And anyone who needs randomness on public blockchain, which is actually right now not very possible, Keep Network makes it available.
Excellent, thank you. Do we have any other questions? Okay, nope. All right, if we don't have any other questions, then I thank you very much for presenting. We can leave it here. We can end here. Everyone, you get about 13 minutes back, and I will see everyone else at the next IPFS weekly meeting. So once again, thank you very much for presenting.
Thanks, Portia. Thanks, y'all.
Thank you.
Thank you. Take care.